Greeting everyone. Welcome to the course on microsensors, implantable devices and rodent surgeries for biomedical applications. My name is Srinivas Bhaskara, TA of this course. In this lecture, let us see what are the kind of electronic systems that are developed for brain stimulation, okay, in rodent models specifically. So, if you look at it, why brain stimulation is required, okay. So, Parkinson disease is one of the neurological disorder in which different symptoms are observed like tremors, slouching, loss of balance, various other things. Now, initially this is treated by using medication. If that does not work, there is something called deep brain stimulation. It is an established clinical therapy for advanced Parkinsonian patients. Currently, these are all the statistics. So many number of people are suffering from Parkinson disease and other stuff. So, in DBS, what is done is this. Okay. So, there is an implant here, and if you look at these structures, okay, they are all electrodes, 1, 2, 3, 4, 4 electrodes are there, and this is supplied with the electrical energy using this biphasic pulse generator, and that particular area in the brain is currently is STN, subthalamic nucleus, is the most preferred choice, and this implant is inserted in this region, subthalamic nucleus, and then electrical signals are applied, and it is observed that the tremors have reduced and some of the symptoms have been relieved. Okay. But there are side effects using this, right. So, there is a need for the neurosurgeons to find out an alternate region for the deep brain stimulation in order to benefit the patients. Okay. So, currently there are different targets like podonucleopontine nucleus, there is a region GPI, STN, of course STN is already chosen, and there is a research going on PPN and GPI, and to find out what will be the best alternative instead of STN. Okay. So, this is the typical application, right. So, what kind of pulses, electrical pulses are required for the stimulation? Let us look into the electrical point of view. Okay. So, if you look at this train, there will be a pulses. Okay. So, generally when I say pulses, this is a biphasic pulse is here. Okay. If I look at from here to here. Okay. So, this is a pulse time period, right. Now, there will be a anodal pulse and there is a cathodal pulse. Okay. This completes one pulse, and there is a second pulse and third pulse like that. So, if I just shrink it, this is let us say one pulse, then there is a relaxation time, then second pulse, then there is relaxation, third pulse, fourth pulse, fifth pulse, like that. Okay. So, in a train, in a pulse train, there will be certain number of pulses. Okay. So, let us say there are 12 pulses. Okay. Just mind you, one pulse will contain anodal pulse, anodal phase as well as a cathodal phase. Okay. So, there is a anodal phase and there is a cathodal phase. Okay. This is what I mean to say one pulse, right, and it will have certain amplitude, current amplitude, and of course, pulse on time, and there is off time and interphase delay in between. Okay. And then there is a relaxation time here, right. So, just let me clear everything and then explain you clearly what are the general nomenclature used for these pulses, right. As you look at it, there is an amplitude here, right, and there is anodic pulse on time and interphase delay. This is the interphase delay between one phase. This is a positive level. Let us say you treat as positive phase, and before the negative phase comes, there should be a time delay. So, typically these are around 100 microseconds, right. This on time typically is 200 microseconds, and this will be around 200 microseconds. Okay. So, in the next coming slides, I have given the reference as well. So, you can just go through and then see what are the parameters. Okay. And this current magnitude will vary depending on the application, right. and your pulse time period, how much would be the time period also varies, right, depending on the applications. Now, how many, this is let us say consider as one pulse, how many such pulses should be there in a train, in a one train, right, like 12 should be there or 13 should be there, 10 should be there, again depends on the application, right. Typically we will take 12 pulses in our applications. So, and then once that number of pulses are generated, again there is a relaxation between the another pulse train. Okay. So, this is called as a pulse time period. Okay. So, typically this is around 1 second or 2 seconds. Okay. I am not concrete about these numbers, but just for you to understand, I am just giving some numbers for a rough idea, right. So, in a 1 second, let us say if I take 1 second as a pulse time period, in that 1 second I will have 12 pulses, means like this. Okay. 12 such repetitions will be there, then there is a relaxation time, right, and again one more pulse train will come. Okay. So, this is a typical the signals, electrical signals, they are used for brain stimulation, right. So, once we are clear about the objective, let us say this is objective, we need to generate these signals for any biomedical applications. These are the some of the parameters one has to keep in mind, right. So, now what are the challenges that we have? Let us say, okay, do not get worried right now, because I just showed you rat, in the earlier side there is a human, right. As I said, there is a research going on finding out alternate target for Parkinson disease, not only for Parkinson, other diseases like Alzheimer's and other stuff. Lot of research is going on, and these concepts has to be proven in animal models before we take it to humans. So, this is where it will become challenging, where the animal, look at, if you look at the laboratory rats and other stuff, their weight is typically around 300 to 500 grams, somewhere around that. Now, one way is you can have a bigger electronic system and have a wire, but if you have a wired system, it is going to harm the natural movement. Okay. So, typically the thing that is required is a wireless, okay, so that it should not harm the animal's movement, the wire should not be hanging from the electronic system. Second thing is charge neutrality. Okay. Of course, we will talk about weight as well. Okay. I somehow skipped this point, but weight is, you can say that less than 10% of the total body weight of the rat, that would be ideal. Okay. So, that rat will not feel like having a overload on the body, okay, which should not harm the experimental outcome, right. I think the sixth point is the weight, right, and also charge neutrality means biphasic pulses. So, as I explained earlier, right. So, you have one phase, right, let us say this is anodic phase and this is cathodic phase, right. Now, once you send this signal to the brain, right, you are pumping some charge into the brain, right. So, after the end of this pulse, the total charge in the brain should be 0. We should not induce extra charge into the brain, right. Now, once we induce the extra charge because of various redox reactions, right, the environment may change, the pH may change, and it may damage the brain as well. So, this is most important to maintain biphasic pulses as a electronic signals that should be given to the brain, right. So, one should keep that in mind. These are some of the design considerations, and also when you look at the current mirroring perspective. Okay. Now, what is this current mirroring? Let us say we have an electrode. Okay, let me go back here. See, there are 4 electrodes here, right. Looks like 1, 2, 3, 4. 4 electrodes are there. Now, you want to stimulate the entire region where the all the 4 electrodes. Okay, you want to supply the signals to all the 4 electrodes at the same time, correct. So, what typically we can do, we have a concept of current mirroring that we will discuss in the coming slides. So, by using current mirroring, you have a source and there is something called current mirroring network. From source the current will be sent to current mirroring network, and current mirroring network generates multiple copies of the current. Okay. So, you have output 1, output 2, you have output 3, output 4, output 5, so many number of outputs that you can have, right. So, the source, if you make it stable, then your output currents may not be stable. Of course, little bit of design considerations on current mirror as well will come into picture. So, if that is taken care, then multiple copies of the current can be possible, right, using current mirroring technique, right. Then now what happens in exploratory research, right, these parameters, okay, the current parameters and all, let us say as I said 200 microseconds as pulse on time, anodal pulse on time, cathodal pulse on time, interface delay of 100 microseconds. In exploratory research, these parameters may not be known in prior. One has to work on that and then see. Even the current amplitudes, let us say for example, I say it is 100 microamperes. So, when you are working on that 100 microamperes may not be sufficient. So, you may need to increase the current to 150, 200, 250, 300, something like that. That means the device, the electronic systems is already employed, right, is already there on the subject, right, without removing it, right, we should be able to program it. Okay. So, that is one of the critical aspect, right, because imagine okay, you have a subject where it is wearing electronic systems backpack and other thing, and you want to take it out, again program it, again put it back, again take it out, again putting it back, okay, it is very tiresome. So, that is one of the critical aspect, okay. And of course, the system dimensions, right. So, typically if you look at laboratory rats, their general body width is around 6 to 8 centimeter or 10 centimeter, and the length will be typically 15 to 25 centimeters, somewhere around that. Okay. So, the electronic system that we are going to use it should be within that particular range, right. So, that it is mechanically intact, connected to the rat's body part. Okay. So, we are talking about some only design considerations, there are a lot more other stuff as well. Okay. So, you talk about for example, power consumption, right. If you want to use a battery, especially for a wireless application, it is energized using battery, right, and of course, there are other methods also. Okay. So, when you use a battery, then it depends on how much power consumption the electronic system is taking, okay, such that you know that how long you will last in the experiment, right. So, these are the typical considerations one can have, right. So, let us look at the system that we have developed in the lab, okay, for biomedical application for rodents. So, typically this is how it looks like. So, let me explain the different things that are present in these slides. Okay. Now, you look at this, a neurosurgeon does neurosurgery and then implant, this is an implant, okay. This is for surface stimulation, okay, cortical surface stimulation. So, if you look at it, the implant shape, it is like a L shape and there will be 5 electrodes in this or 6 electrodes, whatever it is, typically you can take whatever the number it is. Okay. So, typically we have multiple electrodes, right, and there is a contact pad, okay, corresponding to all the electrodes, right. Here we use something called as FPC connector, right. So, there is FPC connector which houses this implant. Now, this is called as electrode interface board. right. So, we have one for right hemisphere, another one for left hemisphere, right, and they are housed by FPC connector, and this is electrode interface board, right. Now, you have an access, there is one more FPC connector here, okay, right, through which you can control the currents that are pumped to different electrodes, right. So, this is electrode interface board as I told, and this is your electronic systems, okay. So, let us say it is typically wireless one, right, and there is a neural implant here, right. So, you can access individual electrode that is present in the neural implant, okay, through an EIB board, okay, and the systems that are required like various ICs such as regulators, microcontrollers, okay, wireless Bluetooth low energy communication based modules, all are present in this, right. So, we will discuss more about this part where we are talking about the architecture of how does a wireless electronic system looks like, but mind you that this wireless electronic system as such is not sufficient, there should be an electrode interface board, or one can also think that why electrode interface board is required, you can directly interface these implant to the wireless electronic system directly, right. Why we do not do that, because the weight of this, okay, imagine this is on the head, right, this is on the head of the rat, okay, and let us say you do not want this is around 20 to let us say around 10 to 20 grams weight of this entire board, okay. So, we do not want to keep it on the rat's head, it will be very heavy, okay, that is why we connect it as a backpack, and there is a electrode interface board. Now, one more advantage with the electrode interface board is, right, suppose you do not want to use this electronic system, you want to use something else, okay. What you just need to have is, you have wireless electronic systems too, you just have some FPC connector, that is all, which matches with this FPC connector that is present on the EIB board, so that you can connect the another board, okay. There is a flexibility to do that, right. So, these are the typical blocks that are involved for brain stimulation. So, let us get into one of the logics, right. Now, here first consideration was, if you look at this one, okay, if you look at this network, okay, this is a basic current mirror network, right. So, if you have if you want to generate multiple currents at the same time, one can extend this where you can short the gate and the sources, and typically you can replicate the same network whatever is here, right. So, to explain briefly how does a current mirror logic works, okay. So, for example, you look at you take a typical resistor and current MOSFET, okay. I am using NMOS here. Now, this is connected to ground, let us say this is 5 volts, right. I am taking 1 kilo ohm resistor or something, right, and because of this there will be a flow of current, right. Now, what is current I? This is mu n Cox W by L VGS minus VTH multiplied by VDS minus VDS square by 2. Okay, this is the typical current, of course, into 1 plus something something will be there, I am just ignoring all that. I am considering a typical current equation, current versus voltage equation, okay. This is your VGS, right, this is your VDS, and we also know that if VDS is greater than or equal to VGS minus VT, then this transistor will be in saturation, right. Now, let us see whether this particular configuration is in saturation mode or not, okay. Now, let us say Vt of this transistor is, let us say, typically 0.7 volt, right. Now, if you look at it carefully, okay, I am just enlarging this. This is VGS, this is the voltage between drain and source, correct. This is the drain, this is the gate, this is the source. Now, since drain and gate are shorted, okay, and source is at the same terminal, right, Vd is equal to Vg, right, because this is Vd, this is Vg, both are shorted, right. So, obviously, Vds is equal to Vgs, right. Now, you take out this equation, whether you check whether Vds is greater than or equal to Vgs minus Vt or not. If this is true, then the transistor will enter into saturation region. Okay. If Vds is equal to Vgs, okay, means these two are same. So, 0 greater than or equal to minus 0.7 volt. Is this condition true? Correct. So, this is true. That means that this transistor M is definitely is in saturation, right. If that condition is not true, then that is in a linear region, clear, right. So, once you are sure that this is in saturation region, correct. Okay, just let me clear the stuff here. We know the current equation right now, okay. Just now we saw that this is the current equation, right. So, the current equation converts as mu n Cox W by L Vgs minus Vt whole square by 2. This most of you know this equation, right. I do not want to get into the details of how it is done and all, right. That means your current is just proportional to Vgs minus Vt. So, it is independent of Vds. This is terms and conditions apply, okay. This is not like 100% true all the time. There is something called saturation effect that comes in later on, okay. So, assuming, okay, your I is proportional to Vgs minus Vt. If you can make sure that Vgs minus Vt of a transistors, two transistors are same, then obviously the currents, let us say your Vgs of one transistor and Vgs of another transistor is same, and make sure that both transistors are in saturation. If we can make sure that this is done, then your currents I1 is equal to I2. The current flowing through transistor 1 and current flowing through transistor 2 is same. So, typically I will just show you one configuration, right. Suppose if I connect two transistors like this, okay. Let us say this is M1, this is M2, this is VGS1, this is VGS2, right. We are very clear that VGS1 is equal to VGS2, right, and we are also sure that M1 is in saturation already with this connection itself, okay. If you short the drain and source, sorry, if you short the drain and gate, okay, this is drain, this is gate, this is source, okay, drain 1 to be clear, gate 1, source 1, this is drain 2, gate 2, source 2. Now, by observing it, okay, sorry, I messed it up a bit, let me clearly draw this. Okay. Okay, all right. Where is my pen? Okay, let us name them transistor 1, transistor 2, drain 1, this is source 1, gate 1, drain 2, gate 2, source 2. Okay. Now, VGS1 is equal to VGS2 because gates are already shorted, sources are also shorted, right. We are very sure that M1 in saturation, these will be in saturation. Okay, let me put some resistor here something, and then let us say plus 5 volts I am applying here, and there is a current flow. Now, if you can make sure whatever the network that is here, okay, if you can make sure this network will take care of the saturation of the M2, right, then the currents that are flowing through will depends on VGS and VGS2. Since VGS1 VGS2 is equal to some VGS, right, the current that flows through is will also be same. Okay. Whatever the current that flows in the M1, the same current will flow through the M2 as well. Okay. So, this is a typical basic current mirror architecture. One can use BJTs, bipolar junction transistors. Since MOSFETs are preferred because they have 0 gate current compared to BJTs, right. So, this is how the typical current mirror configuration looks like. So, we try to replicate the same, right. So, where is pen? Okay. Now, let us say the current flows in this is 200 microampere, same current flows in this. Okay. So, one can observe here, I explained the concept of current mirror using NMOS, but we have used the PMOS here. Okay. That is typical, like it is trivial that you can understand that you can use either NMOS or a PMOS depending on the application. Here we used PMOS for this particular application where we want to reduce the number of transistors. Okay. So, let us say 200 microamperes flows through M2, same 200 microamperes flows through M1. If you can make sure that M1 is in saturation, M2 is already in saturation. Okay. Now, this is a current mirror logic. Now, finally, ultimately what is that we are going to generate? We want to generate a biphasic pulse. Okay. So, let me erase everything. Okay. So, you need to generate this. Okay. Let us say this is a biphasic pulse, right. So, across the load, right, across the load, let us say between the electrodes E1 and E2, okay, we need to generate a biphasic pulse. So, these are the switches, okay, these are SPDT switches, okay, single pole double throw switches. Okay. You can think them as a 2x1 multiplexer or something like that. Okay. You have two outputs, right, and there is a pole, okay, this is output 1, output 2, right. So, in switches terminology they say NC1, like normally closed, normally open, okay, COM, something like that. But if you look at it, it is like a simple 2x1 multiplexer. And there is a select line and there is a input, right. So, based on the select line, the input will be transferred to either O1 or to output 2, right. So, what happens is if I chose, okay, so let me erase again everything, right. Now, what we are doing is to generate biphasic pulses, we are changing the pulse positions in one pattern in a way, okay, such that current flows from VDD to the ground, okay. If you look at E1 and E2, now the current is flowing in this way, right, and there is another way where the current flows in by properly programming the switch positions, the current flows in opposite direction, right, and these switch positions are controlled by using GPIO pins, right. Now, the currents, how the currents are generated is by using a IDAC block, okay. Constant current digital to analog converter blocks will be there, they will generate the current, right. since this is in saturation, right, and these two are connected in series, whatever the current flows here, the same current has to flow, right. If you can program your microcontroller to generate 200 microamperes sync current, same 200 microampere sync current flows from VDD via transistor to the IDIC block, right. And if you can maintain this guy in saturation, then the current flow will takes place by properly switching the positions. In one way the current flows from E1 to E2, in another switch positions the current flows from E2 to E1 this results in generation of a biphasic pulse. Okay. Typically how that can be done I have shown you here, we will discuss in the next lecture. Thank you.